Hello and welcome back to the official CertCop series. We're continuing on with our first module in the Domain 1 in the Linux Plus, the CompTIA Linux Plus course. Why are you here taking this course? Well, we've talked about in the intro some of the benefits of Linux. In this module, we're going to talk about in this module the basics of Linux. We're going to talk about Linux fundamentals. These are going to be the building blocks that are going to form other topics and other concepts for other modules in the future. So you want to understand this module very, very, very well. There's a time to take lots of good notes. This will be one of the modules to do so. So these are our topics. We're going to summarize Linux fundamentals. We're going to go into about the Linux file system hierarchy standard. We're going to talk about the boot process of Linux. We're going to look at kernel panic. We're going to look at some of the different device types in the /dev folder. We're going to talk about compiling packages from source. So the one benefit to Linux is that everything is open source and falls under the GNU GPL license. So many packages are required to provide the source code. So the source code lets you build pretty much any binary that you would ordinarily install. You can build it from source code. We'll talk about some different storage concepts. We'll talk about how to list out hardware information. So we'll talk about the FHS. We'll talk about BIOS. We'll talk about the Grand Unified Bootloader, or GRUB. We'll talk about file system and user space, or FUSE. And we'll talk about RAID. RAID, the redundant array of independent or inexpensive disks. Let's talk about first and foremost the file system hierarchy standard. This is the system you will see. And when you look at the file system in Linux, you will see these folders. How do we view this in our virtual machine? Well, if you haven't looked at a virtual machine before, we're going to open up a terminal. And what we're going to do is we're going to click CD space / That's going to put us into the root directory. Now we can see all the different folders that we're about to talk about. If you see a bin, like a blue icon with an arrow, it just means it's a pointer. But most of these other ones, we have boot, we have CD-ROM, we have dev, etc, home, media, mount, opt, proc. These are all standard folders, and we're going to see what each one of these folders does in Linux. So the boot folder. This boot folder has the files related to the boot system, the boot directory. Then you've got the proc folder. The proc folder has things related to the system data, the kernel, and of course processing data, hence the term proc. The /sys directory, these are files that contain system related information. /var directory, this is going to be data that changes, it's variable. This is going to be your logs are going to be in this directory. You've got the USR directory. So many subdirectories that contain executables, libraries, and documentation. You got your critical libraries directory, your /dev, so your files that represent physical devices. Remember, everything in Linux is a file. Every folder, every device driver, every device you plug in will be represented as a file. So you have the etc directory. etc directory has critical configuration files for the system. You have the opt directory. These are optional software packages, things you might not see necessarily. Maybe you install Docker or something like that as an optional component, or something along those lines. Then you have the bin directory. Bin, again, it's going to be your critical binary executables. You got the sbin directory, your system binaries. You got the home directory. That's going to be where most of your user files are at. Your media, so any types of removable media, this is where you'll want to mount your removable media. MNT directory, this is designed for temporary mounts, but you may use it for other things. The root account, which is the home directory for the root user. And then you have the /tmp, which is temporary files. So here's what the file system hierarchy standard looks like. So you got the root directory. Every single file and directory starts from root. Only the root user has the rights to write under this directory. So root is the user's home directory, which is not the same as /. So we go to back over to our terminal here. Notice we have the root directory, which is not the same as the current directory that we're in. We type in pwd, present working directory, we are in root. If we change into root, notice we're not able to because we have not elevated to root yet. Now we are able to change into that directory. Now we're actually in the root directory. So there's the root bash folder, the bash history, much like a user profile, but with a few extra things. So we have the root directory, and then we have the bin directory. So the bin, that's going to be your essential, your system binaries, these things that need to be available in single user mode, such as your cat command, your ls command, and your copy commands. Let's go look at the bin directory. So a lot of different commands. Your grep commands are in here. Systemd commands, tcp dump. So these are Linux commands you need to run in single user mode. Let's look at the boot directory. So if we go back here, we're working our way across. We've got bin, we've got boot directory. So the boot directory has bootloader files, such as kernels and the init runtime daemon. So if we clear the screen, there's our different kernels. Init runtime daemon. Our generic config. So inside the boot directory, you have the kernel init runtime daemon. You have the VM Linux files. You also have in here the grub files, the grub directory. We'll see that a little bit later. Then we have the dev directory. What is the dev directory? Dev is short for device. So you may see it /dev/tty. You may see it something else depending upon your flavor of Linux. Here's all of your devices. Your TTYs, SDAs, 1s, 2s, and 3s. Your loopback devices. Then we have Etsy. Etsy, an important directory because it has system-wide configuration files. So it contains configuration files required by all programs. Also has startup and shutdown shell scripts to start up individual programs. You've got Etsy. For example, the resolve.config file and many other files. You got the Wireshark folder in here. You've got Apache is in here. The Etsy shadow file. The Etsy sudoers file. Important configuration for your passwords. You got mod probe for your kernel modules. You got your D package, your FS tab file, your cron. So lots of important stuff in your Etsy directory. Then you have the home directory. This is going to be the individual users' directory. So if we go to the home directory, so we have all the different accounts that are created so far. The home directory is for users to store personal files. Then you've got the lib directory, lib, for libraries. So these are essential libraries for binaries for bin and sbin. So there's your different binaries that you need. Media directory. The media directory, that's going to be your mount points for removable media like CD-ROMs, temporary for removable devices, your floppy drives, etc. Right now we have one for USB. We have this one for CertComm. And we have our lost and found files in there. We've got our external thumb drive with currently nothing on it. Your MNT directory. This is going to be temporary mounted stuff. So CD-ROMs, it could be anything you want to temporarily mount there. This is going to be more likely where sysadmins can mount file systems as well. Right now, there's nothing in there. MNT directory is currently empty. Then we have the opt directory. Opt directory, optional application software packages. So things that are add-ons from vendors. Add-ons should be installed under the opt or opt subdirectory. Then you have sbin. The sbin directory falls under USR. So sbin, this would be your essential system binaries, your file system checker, your route command, your init command. It also does have binary executables as well. So we're going to go ahead and change directories. Some of your logical volume management stuff. User delete, user mod. That's your unshadow file. Swap on, swap off. A lot of essential binaries there. Then you have the /srv. This may vary depending on which Linux distribution you're using. So right now, nothing in this particular one on Ubuntu Mate. You have your temp file directory, your TMP. That's going to be in your var/TMP. Then you have a regular TMP at the root level. The temporary files often not preserved between system reboots. This is contemporary files created by system end users. The files under this directory are deleted when the system gets rebooted. You've got the USR directory. This is mostly only going to be user data. So if you can't find a program under bin, look under USR/bin. If you can't find a binary under sbin, look under USR/sbin. So notice we have sbin, and then we have USR sbin, and we have USR/bin. So important to recognize the distinction between them. And you have the proc directory. Proc directory got different processes there. So this is your virtual file system providing process and kernel information as files. So Linux corresponds to a prox mount, generally automated and populated by the system. So you won't have to really mess around here too much. But we'll see a few commands here, things like uptime. So the uptime command is in the proc directory. Now, there may be other directories not covered here, but we covered the most important ones for the Linux file system. Let's talk about the basic boot process. Let's talk about the boot process. So what is a bootloader? A bootloader is a piece of software designed to handle booting an operating system. Up until recently, we had mostly what they call BIOS, basic input-output system, and essentially you could find the BIOS inside of the master boot record. So commonly in Linux, you've got dev/HDA or dev/SDA contains the MBR. So master boot record, depending on whether or not you're booting from a thumb drive or a CD-ROM, that will change. If you're booting from a live Linux distribution, it will be a little bit different in the process. So then we have, besides BIOS, largely has been replaced by UEFI, but the term is still hanging around. In case you hear it, just know that it's the basic input-output system which loads the operating system. Then we have grub. Grub, when you boot up your Linux box, you frequently encounter the grub splash screen. This is a small menu where you can choose from a few alternatives. So if right now I were to go in and reboot my Ubuntu distribution, we should see a grub screen temporarily. Sometimes the grub screen will be hidden unless you hit a certain key combination. So you can pick the kernel image that you want your system to boot from if you have more than one kernel installed. So the kernel is chosen by grub, mounts the root file system. If I hit the escape key, then we can start seeing what's happening during the boot up process. That was still in the process of shutting down. So it's loading up all the system services. This particular version of Linux doesn't have a separate grub screen, but essentially at this point, once you've reached this point, your system is booted up, it chooses the kernel, it mounts what's in the grub.config file, and then you have the init. The init's run level program. So you would be looking for normally for an init file located at the etc init tab directory. So there are different run levels in Linux. You might see different services starting out depending on the Linux distribution you've started, you might see, for example, that your mail service is starting up or something along those lines. So let's talk about BIOS versus UEFI. So BIOS is the chip on the motherboard that runs when the system gets turned on. It controls the flow of information between the operating system. Largely, this will be outside of your control, depending on the type of computer that you have or the type of motherboard. But it looks at things like the operating system, any attached hardware, keyboard, mouse, and even printers. UEFI has a few extra features. Ultimately, is working to replace BIOS, but there's also legacy boot options in UEFI that still work kind of similar to how BIOS works. So we keep it in the certification for right now. So UEFI has new features like secure boot, the ability to boot multiple operating systems securely through a trusted platform module. UEFI also has been criticized for making it more difficult to install secondary Linux operating systems. So it's important to understand that not all Linux distributions will support UEFI. So if you have an older laptop or an older system, you might be more wide range of supported Linux operating systems than UEFI, but most of the major ones are going to be supported by UEFI. Then we have the MK init runtime daemon. This is the initial image that the kernel uses to essentially preload any block device modules, such as IDE, Integrated Drive Electronics, SCSI, Small System Computing Interface, or RAID, required to access the root file system. The MK init runtime daemon automatically loads the file system modules, the ext3, all SCSI host adapter lines in the modprobe.config file, and any RAID modules if the system's partition is on RAID. So this is making it easier to design and utilize modular device drivers inside of kernels. So here's the example grub bootloader. So typically installed during the boot process, but it's conceivable that the bootloader could become corrupted. So it's possible to reinstall grub using the grub install command or the grub2 install command. So we have our Ubuntu system here. We'll look at the grub install command. There's also a grub config file, which we'll talk about in the next slide. So grub install grub to a device. So you can install it to a hard drive, you can install it to a removable drive. You have grub make config, and you also have grub install. So an example command might be, let's say we have SDB1, so you would do grub -install dev SDB1. We have sudo. So the file system doesn't support embedding, gave us a warning, embedding is not possible, this is required for a RAID install. So if we do grub2 install, so that one is not found on here. So sudo apt-get install grub2. So doesn't have a grub install, there's also grub-make config. So this will allow you to generate a grub configuration file. So grub2 make config, which is used solely for grub2, creates grub2 config files from the etc directory structure. The grub2 update command lets you execute grub2 make config programs different ways. Primarily reason for the grub2 update command is if you have to ensure backward compatibility with systems that have not been updated yet, or systems that are updating their config files. So Drcut. Drcut is a command used to enhance Linux boot systems functioning and develop a Linux boot image, init RAM file system, or initial RAM file system. This will copy equipment and documents from a mounted system and integrating them with a Drcut framework. Now, Drcut is not installed on all distributions, but so if you have to install Drcut, you'll first have to install it. So let's say you're working with a mail system or enterprise system, you might have to install this platform. Now we've installed Drcut and we can run it. The simplest, most easiest command you can run. You can run Drcut. So you'll have to override the initial init RAM file system if you want to with the -- force command. We're not going to do that here, but again, that is another option for running your initial startup. So let's talk about the init runtime daemon. So normally there are only a few things mounted by default. Additional modules will have to be necessary during the boot process before file systems may be mounted. These extra modules are kept in a compressed file called the init runtime daemon.img. Then we have the VM Linux directory. So the boot directory contains the VM Linux file. Each kernel version contains a unique VM Linux file, which we can go to the boot directory. And we can see currently we have the generic one, and then we have vmlinux.old. We also have the init runtime.img, and we have the init run img.old. So the Grand Unified Bootloader, GRUB. The bootloader software that supports many operating systems and allows users to choose between them during startup. Eric Stefan Bolian invented GRUB, which was later developed as GNU GRUB under the GNU project. Original package known as GRUB Legacy is still available for download, but is no longer actively being developed. So GRUB alludes to the Grand Unified Theory of Physics. GRUB 2 supports more boot devices, more configuration files, logical volume management, and software RAID. It also supports UEFI and EFI. PXE, or Pixie Boot, as it's been called. Pre-boot execution environment. This lets you boot to a system via a network. Presuming that there's been a boot server set up, the PXE boot obtains network configuration information such as an IP address, subnet mask from a dynamic host config protocol or DHCP server. So if you don't have a boot source, in many cases Linux will boot into a PXE environment to try and pull from a network. Booting from ISO or USB. So there are various live Linux distributions that let you boot from a CD. Pretty much any Linux distribution will let you try out Linux before you buy it, so to speak. So you're booting from an ISO. because the file type used to store the operating system is called an ISO. So some of the tools you can utilize to work with ISOs, you've got Rufus. This is, of course, a Windows tool, but it does have versions for other operating systems. It has a portable version and one that runs on GitHub. So you pick your version of thumb drive that you want to create, download your ISO of Linux. You can go to distrowatch.com and pick from all kinds of different live distributions that are out there. Many more distros than we have time for in the scope of this course, but again, that's the beauty of Linux, is that there's so many options, and new distributions get released all the time. So if you want to boot from a thumb drive or boot from an ISO, this is a good way to do that. So you can burn your ISO to a USB drive and go from there. You could also use the DD utility as well. So then we have kernel panic. So when something goes wrong with the system crashes, resulting in what's called a kernel panic. So data is often saved using a feature known as kdump. So this can be viewed by a kernel specialist to discover the reason for the crash. Kernel failures happen when the Linux kernel stops running in memory, causing the system to crash. So kernel panics can happen because of software changes. They could be a result of installing a new kernel without the appropriate module, or library changes, or starting or stopping a program at a new run level. Often these times of boot errors can be fixed by starting the system in an alternative way and editing the files to change the system. Let's talk about some of the different device types in /dev. So the devs folder includes device files, which are used to access physical and virtual devices like hard drives, keyboards, and CPUs. The dev system is memory-based and is not kept on a hard drive. So Linux supports 3 types of devices: character, block, and network. We're going to talk about the different types. So character devices are read and written directly without buffering. For example, so system serial ports. Block devices can only be written to and read from in multiples of block size, typically 512 or 1024 bytes. Disk names are alphabetical in Linux. Dev SDA is the first drive, SDB is the second hard drive, and so on. So we have block devices. So block device reads and writes data in chunks. So that is blocks rather. Storage devices, for example, your USB hard drives, CD-ROMs, and DVDs are examples of block devices. A character device is a device that reads and writes data in single bits or single characters. A keyboard is an example of a character device because it only communicates one character to the system at a time. And character devices can be read and written to without buffering. For example, the system serial ports dev CUA0 and dev CUA1. So let's go look at our dev directory. So we have character devices, we have block devices, we have disks, we have loopback devices. So block devices can be more accessed via their special file, but are more commonly accessed via the file system. Block devices are probably more likely what you're going to be working with for the most part: thumb drives, hard drives, etc. So then we have device files. So device files do not reflect genuine physical characteristics. These are known as special character devices. Linux dev null is a device file. This will throw away whatever is written to it and return end of file when it's done. So pretty much anything you put into dev null will be erased. The dev 0 is a special file that returns null characters, frequently used in conjunction with programs such as the DD command to produce big files. Then you have the dev urandom, which is basically a function for generating random numbers, otherwise called a pseudo-random number generator, usually utilized for software development, cryptographic purposes, encryption tools. It basically reuses the internal pool to produce pseudo-random bits, and provides an interface to the kernel's random number generator, and has major device number 1 and minor device number 9. And how do you call it? Well, you can see random right here. And then you can see urandom. So random and urandom, kernel random number source devices. So here's an example of using it with commands. So you can change ownership, random. So if you want to write something to random, we're talking about entropy here. So generally, when your system starts up without much operator interaction, the entropy is in a fairly predictable state. So there's less noise. By using the random number generator, you introduce more entropy into the system. Again, that's a bit more beyond the scope of this course, but something to be aware of nonetheless. Then we have to talk about configure files. So some of you guys have probably run a configure file installing some package from source code, but wondered what it actually did and how it works. So the configure script, or the ./configure script, is responsible for getting ready to build software on your specific system. Make sure all the dependencies for the rest of the build and install process are available. And it finds out whatever it needs to know to use those dependencies. Unix programs are often written in C, so usually you'll need a C compiler to build them. In most cases, the configure script will establish that your system does have a C compiler and find out what it's called and where to find it. In Linux, most oftentimes you'll have the GCC compiler. So GNU, Project C, and C++ compiler. So when you invoke GCC, it does pre-processing, compilation, assembly, and linking. So this will generally, the configure file will find this compiler and will be able to use it for you. Then we have the make file. So certain activities are done with the make file. So the make command is a utility for creating and managing programs. Source code gets used to create programs and other sorts of files. One of the key parts of the make utility is to decide which parts of the program must be built or recompiled, and to issue the instructions required for recompilation. So software developers create a make file to accomplish the development of their software project. So once the configuration file has done its job, we then invoke the make file. Tarballs you download may not necessarily have a finished make file, so instead it will come with a make file template and a configure script that produces a customized make file specific to your system. Then we have the make install. So the install option is intended to install code from source on a system depending on how the software developer designed the make file. It may also include a build procedure. Now the software is built and ready to run, the files can be copied to their final destinations. The make install command will copy the built program, its libraries, its documentation to the correct locations. Usually means that the program's binary will be copied to a directory on the path. The program's manual page will be copied to the directory on your man path. Any other files it depends on will be safely stored in an appropriate place. So then we have file storage. Let's talk about some of the different storage. This is important not only for Linux, but also for the cloud, because largely the cloud storage tends to mirror Linux storage in many ways. So we first have file storage. The local system uses an external storage device for file storage. Your network file shares. Shares the distant storage device to the local system, and now users can store files and directories on a remote system using NFS, SMB, or Common Internet File System. Block storage. Block storage device is a type of physical storage device that's commonly used to provide back-end storage for Linux systems. So block-end storage would be your traditional SATA drives, SSDs, RAID drives, and any storage area network devices. Remember, the block storage writes the data in blocks. Then we have object storage. Object storage is not really a Linux idea, but it's common in cloud infrastructures. Linux may employ object storage on a cloud infrastructure, and the storage type is quickly becoming a popular way to store and transfer data. So object storage arranges data into groups rather than using files and typical file characteristics. Partitions. Let's talk about partitions. Partitions separate hard drives into smaller components. Each component can be treated as a different storage device in a separate file system. You've got BTRFS, you've got XFS, ext4, and so on. The partitions you typically may create is limited. Originally, only 4 partitions, referred to as primary partitions, were permitted. Then we started getting into extended partitions. So by default, only the root user has the ability to create file systems, as it should be. File system user space is a Linux kernel feature that allows ordinary users to construct Linux file systems. So if we want to work in Fuse, you have to have a few things first. So we have to install Fuse because it may not be installed on certain Linux distributions. Let's open up our terminal, change back to our home directory. We're going to first make sure that our system is up to date. Sudo apt-get updates. Then we're going to sudo apt install Fuse. So we'll say yes. That'll take a moment to get Fuse installed. Then we're going to have to add the user accounts to the Fuse group. Now that we have Fuse installed, all we have to do is go in and add our users that we want to be able to access Fuse. So we're going to add in Fuse to our Fuse group. Certcop. First, we got to create a Fuse group. Sudo group add users. Now we'll do also add Neo. Now we have our fuse.config file. And we can set our different permissions as needed. Now we're ready to go. Ready to set up Fuse on Ubuntu. So not too many steps. And users can now be able to construct file systems without having to do a whole lot of swapping and mounting. So let's talk about RAID, redundant array of independent or inexpensive disks. RAID is a redundancy feature. RAID is not strictly unique to Linux, but redundancy is provided by a RAID device. Here we have two or more physical devices that can be joined to form a single device that stores data in such a way that minimizes data loss. So you could have data being striped, you could have data being mirrored, as we'll see in the next few slides. So disk striping, often called RAID 0, this is the technique of writing several drives as if they were a single device. Striping is used to accomplish writes, so the speed is paramount. So you write some data to one drive, then write some data to another drive, and so on. Striping, unfortunately, at RAID 0 has no redundancy. Strictly is a speed-saving matter. Mirroring. Mirroring, often called RAID 1, makes two or more drives seem to be a single storage device, but we have essentially a copy. So when you write one drive, then you make another copy to another drive. So the problem with it is you're losing half your storage space, but you are getting some redundancy. So this is called RAID 1. So you have disk mirroring and disk striping. Then we have parity data. So parity data is obtained from the data saved on the RAID's devices. So let's say you have three drives, A and B, and then you have a C. So a drive C might hold the parity data. So if device A fails, it could be rebuilt using the parity data on device C. RAID 5, for example, is disk striping with parity. Requires three drives at a minimum and stripes the parity across the different drives. So if any one of the drives fails, the parity can be rebuilt. If you put all your parity on one drive, then you have a single point of failure, which is what RAID 4 is. So then we have LSPCI. So the LSPCI command displays information about data attached to the PCI bus. So this means it's bus-centric, means it displays line numbers. So if we go to our terminal and we go ahead and clear the screen and we type in LSPCI, we will get each line number. You've got your host bridge, your Intel, you got your ISA, your IDE, your VGA, Ethernet controller. We got some VirtualBox stuff, a USB controller for your mouse, bridge. So these are all, for the most part, virtual. If you do LSPCI-VVV, it gives you more verbose information. If you do LSPCI NNN, gives you a little bit more concise. It displays both device numbers and names. So 3 V's is the most verbose, 3 N's gives you the line numbers and the names. So there's the man page for LSPCI. So if you're going to report bugs in PCI drivers, they even tell you which command to use. Some of these outputs will be much beyond the scope of this course. You can do LSPCI-T and display a tree-like structure. So you have different options with LSPCI. What about LSUSB? This displays devices that are attached on USB buses. So LSUSB, let's go ahead and look at the man page. A lot of times you might use these utilities if you're having problems getting devices to recognize. LSUSB is for displaying information about USB buses in the system and the devices connected to them. So if we do LSUSB-V for verbose, LSUSB, it will give us all kinds of information about the root hub, the bus, how it's powered, its class, protocol type, lots of information. So if you want to display a specific device, LSUSB-D, that will show you a specific device. You can also do LSUSB-T, show it in a bit of a tree-like structure, a little bit easier to read. And of course, V for verbose. So you got bus 2, port 1, device 1, bus 1, port 1, device 1, bus 2, port 1, device 1. Then we have DMI decode. This is called Desktop Management Interface Table Decoder. This can read data from a DMI table used to collect system hardware information such as your processor, memory, serial numbers, BIOS, etc. in a readable manner. Let's go ahead and look at the man page. So some say SM BIOS, which is the old term for it. So we're going to go ahead and do DMI decode. I'm going to pipe that to the head command. And so we have to sudo. So SM BIOS 2.5. And it has vendor information. Of course, it's a virtual box. So you're going to have a little bit different on your system than likely will be listed here. So we talked a lot about Linux fundamentals. We talked about the file system hierarchy standard. We talked about directories, directory structures. We talked about the boot process. We looked at kernel panic if your device has a problem. We talked about different device types. We looked at some storage options, block storage, device storage. Talked about some other storage concepts. And of course, some different ways to list hardware information, LSPCI, LSUSB, and DMI decode. So that concludes this first module. I appreciate your attention. We'll see you in the next one. Thank you.